We're continuing here with some answering of the questions that are in the EKG lab. And the first question here is explain the changes in heart rate between rest and exercise. I think we're all clear that in exercise the heart rate goes up. The physiological mechanism causing this change would be that, well, your muscles are demanding more oxygen, so you need to deliver more blood, oxygenated blood to the muscles, and for that you need to increase your heart rate to increase your cardiac output in order to meet the new demand. What changes occurred in the duration of systole between resting and post-leg exercise, or any exercise for that matter? Systole does not change in exercise, not much anyway. So the changes in the duration of systole between exercise and rest is not much at all. Now, when you're talking about changes between in this diastole between rest and exercise, diastole is where you're going to gain the time for the extra QRS complex or the extra systolic events of your heart. So diastole, of course, changes a lot when you are exercising. And so when you compare that between rest and exercise, there's a big change. Diastole is much shorter in during exercise as opposed to rest. When you're reviewing the imaginary data, is there always a P wave for every QRS complex? That hopefully would answer yes. That is, the shape of the P wave should be a small upward deflection like this, and the T wave shape should be a little bit larger upward deflection like that. So this would be a P wave, this would be a typical T wave. Is there baseline drift in the recording? A lot of times we do have that, but well, we're doing imaginary here, or it's not, you didn't record anything, so hopefully there was no drift in the recording, meaning that the baseline would just go up like this or something like that. That's not good. Do you have any record in the noise in the recording? I'm sorry. And that would be noise in the recording would be just a flickering line like this, and it might drift as well, so noise would be looking like that. And sometimes noise can be quite severe. It could be literally like this, that you have squiggly lines like that. Okay, so these questions here we can't really answer because we didn't do all of this, but here now let's take a look at the mean electric axis determination. Really all you need is leads 1, 2, and 3. So we're going to just take a look at 1, 2, and 3, and really all you need is the mean net QRS amplitude, and you really only need that for lead 1 and lead 3. Oops, this one did not turn out good either. So let's make a nice little asterisk. Okay. The augmented leads we don't really need for that, and you will see why. So the measuring the QRS and then sort of subtracting the Q and the S from the R, it's not really that meaningful. So what we should do is go from the baseline and measure. So instead of, let me just draw this here. So this would be Q, R, S, and then we're going back to the baseline. Instead of subtracting this little squiggle from the baseline, that's here is the Q, and that little squiggle from the baseline, that is T. I'm sorry, that's S. We're just going to go cut this whole thing across and measure just the amplitude of your R wave. Okay, so the mean net QRS amplitude, let me just give you some imaginary data, and that'll be for lead 1. Let's say we are at 0.4 millivolts. The amplitude, let's say it was positive. And for lead 3, let's say we have 0.8 millivolts, also in positive. Now what are we going to do with the data? These are the only 2 data pieces that you really need. And now we're going to go into this diagram right here for lead 1. So let's just go back for this real quick. For lead 1, our net QRS amplitude was 0.4 millivolts. So that is right here. Lead 1 is going straight across right here. Oops, let me take this off. And so we were in the positive, so this would be lead 1 in the positive. And so if the radius from here to here is 1 millivolt, we were just under half. So that would be the mean electric axis, or the mean magnitude for lead 1 would be approximately to here, so 0.4, something like that. And for lead 3, this one here is our lead 3 right here, the one that goes down to 120 degrees on the circle, if this is 0. So for our lead 3, the vector, we said that was going to be 0.8 millivolts. So now we're almost full circle. If one radius is going to be 1 millivolt, we're going down here toward the positive on lead 3. So let me just draw this, and I'm just eyeballing this. So our vector would be going to here approximately for 0.8 millivolts if the full radius would be considered 1 millivolt. Now we have our two vectors in here. Now we need to draw perpendiculars. So I put the perpendiculars to these vectors in here for you. Again, the lead 1 magnitude was positive 0.4. The lead 3 magnitude was positive 0.8. Of course, these are all just estimations, and then the green line here, the dotted line, will be the perpendiculars that have a 90-degree angle to all of this. So this would be 90 degree, this would be 90 degree, approximately. Now, the way you're finding your mean electric axis is by finding the perpendicular of these two, the intercept of the two perpendiculars right here. And then you would take going from the center of the circle, and you're going to extend that until you find that intercept. And so basically we are going down this way, so until we reach the intercept here of these two perpendiculars. And as it turns out, our mean electric axis for this particular situation here, so we're dealing here with, this is 60 degrees, this is 90 degrees, so we can safely assume this is 70, 80, 90, so this would be 70 degrees. So your mean electric axis would be at 70 degrees. The magnitude is beyond 1 millivolt because we said one radius length was 1 millivolt, so we're a little bit above that. I don't know, let's just eyeball this. I would say about 1.3 millivolts. And that should be pretty much accurate. So this is how you find your mean electric axis and the magnitude of it. The axis is interesting because it tells you pretty much anatomically which way is this heart sitting in the chest cavity, because the mean electric axis pretty much resembles the path of the interventricular septum, where the most of the electric activity goes down. Now to finish up here, let's take a look at the questions. Define electrocardiogram here on 10. That will be a recording of the electric activity through the heart from different perspectives, which are called leads. On 11, define Einthoven's triangle. That's a configuration of 3 leads, lead 1, lead 2, and lead 3. What factors affect the orientation of the mean electric axis in a healthy heart? That's basically your anatomy. How much space is there? How much hypertrophy maybe is there on the right or the left side? How much space do the lungs need? So basically anatomical factors that are playing into the orientation of the mean electric axis in a healthy heart. So it's the main direction that your interventricular septum takes. Number 13, what factors affect the morphology of the QRS complex when recorded on different leads? So the morphology or the shape of the QRS complex when recorded on different leads, again, those are anatomical factors. If my heart sits in my chest cavity, pointing down slightly to the left, then my lead 2 will be my strongest recording. because it lines up with the electric activity as it goes down the interventricular septum. Now, if my heart is very much pointing to the left, then my lead 1 will be my strongest EKG tracing. And if my heart points down, maybe even slightly to the right, then my lead 3 will be the best recording. So the morphology or shape of the QRS complex depends really on which direction your interventricular septum points. Now 14, that's important, what is meant by a left axis deviation and what might cause this. So left axis deviation, there will be a mean electric axis that points in this direction up here. So, oops, not a very good arrow, but it's pointing up here. And that means this is not normal if we're going above the 0 right here. One of the reasons that might cause this would be that the right side of the heart got too big and it's kind of pushing over the left side of the heart, and therefore we're going to have a left axis deviation. Now, so the cause for this would be typically right ventricular hypertrophy. The right side got too big. Maybe a pulmonary stenosis, a pulmonary embolism that has caused this, that the right side was overworked. It's pushing against a big resistance. It got big and now it's pushing everything over to the left side, so left axis deviation. What is meant by a right axis deviation on 15 right here, that means that we are going past what's normal here on the right side, and that would mean that I'm going past here this direction with my mean electric axis, definitely past the 90, about 110, 120 is sort of the borderline, and then you have a right axis deviation. What might cause this? Typically the biggest suspect would be the left ventricle being too large. Maybe you have a aortic stenosis that's causing the left side of the heart to work extra hard, pushing against the resistance. It got big because muscle gains when it has to work over time. So the left ventricular hypertrophy pushing everything over, and then you're going to end up with a right axis deviation.